Kia ora, and welcome to the second exciting episode of doing questions on mechanics level 3. Hopefully today the little gremlins are going to be worked out. I don't have a webcam so you can't see my lovely face, but who cares. We're going to go through circular motion today. So if you remember, or if you go to your Schoology page and get up the revision side, I'll just do it myself here. So if you go into Schoology and you go into your 4 Forces class, boom boom boom, and we go into our mechanics revision folder, we're going to do the circular motion stuff today. So we did the translational motion the other day. I think I might do that one again because it was a bit crap. This is the sheet that we're going to be looking at today. So again, if you've got your own sheet, just go through all of these equations and make sure that you know what the symbols mean and what the units are. So I'll very quickly go through it myself here. I'll just go switch this little page. XCOM is our center of mass equation. Mass of 1, distance of 1, plus the mass of, well, that should be mass of 2, distance of 2. So I'll just fix that while I'm here. Divided by the mass of 1 over the plus mass of 2. And remember that the distance from one thing might be 0 because we're going from the center of it. This is the centripetal force equation. So the centripetal force is equal to the mass times the square of the velocity divided by the radius of the circle. We've got our gravitational force equation here. We've got our gravitational constant. This is given to you on your resource sheet, multiplied by the mass of one object, the mass of the thing that's being orbited, and then the mass of the thing that's doing the orbiting over the radius squared between the two. FC and FG are often combined, or not combined. FC is often equivalent to the force of gravity, which I'm going to be talking about down here. And the other force one that we don't have on our sheet is force weight, which is equal to mass times acceleration. However, on our sheet we do have, if I bring it over there, force is equal to mass times acceleration. So that one we have, we have got this one and that one. Okay, so these three ones are the ones that we need to keep in our mind, and we need to remember that the acceleration in this equation is quite often the acceleration given by gravity. What do we need to know? Gravity is the centripetal force in satellite motion. So when I'm talking about satellite motion, we are talking about things that are going around. So a satellite in orbit of a planet is usually what we're talking about there. The radius is from the center of the planet. So we'll see in a little while that quite often they give you two distances. They'll give you the distance from the surface of the planet to the satelliting thing, and then they'll give you the radius of the planet as well. And you have to add those two things together. It's a stupid trick that they play every single year. Geostationary orbits are an orbit that has a period of 1 day. It has to be over the equator of the planet. So if the planet is revolving around, maybe I'll draw this. We'll just go, I'm going to do, oops, what have I just done there? Typically, I'll just go to this page here. So hopefully you can see this. So if we have a satellite, which I'll draw badly, that's orbiting the Earth. The Earth is going to be spinning around. So this is, we're looking down on it basically, and the satellite is going to be orbiting around the Earth. If it's geostationary, it means that the satellite is directly above a point on the Earth. So if this is, oops, what's going on here? If this is New Zealand down there, and I want the satellite to be directly above, because I'm going to use it for beaming 5G radiation down and giving us all COVID, I want it to be in the same spot over the Earth. So it has to be over the equator, and it has to be spinning at the same, or it has to be rotating around the Earth at the same, with the same period as the rotation of the Earth. And we know that the period of the rotation of the Earth is 1 day, 24 hours, 24 times 3,600 seconds. Okay, back to our little sheet again, if I can find it. The velocity of the satellite determines the orbit. So the relationship between the period and the radius and the velocity is going to be the thing that determines the orbit. We're going to use Fc equals Fg to work out that you don't actually need the mass of the thing that's orbiting the planet to determine the orbit. We'll do that in one of the questions in a little while. So that's satellite motion. The other type of motion that we get is banked curves, and there can be two types. We can have like a plane type thing or a car on a bank. These are quite the most common ones here. And we'll have a look at the different components. The two solid lines here are the ones that we are usually given or we can work out. This is the weight force, which acts straight down of any object. It's always going to be acting towards the center of the Earth, straight down. The resultant force, the normal force or the support force or the reaction force is going to be acting at 90 degrees to the surface. So the car is on a surface which is on an angle. The normal force, the reactive force, the supportive force is going to be pushing back at 90 degrees to there. The reactive force is going to be the big one. And then we've got a third force, which is the unbalanced force, which is the centripetal force, and it acts towards the center of the circle. So again, if the car is going around in a track, it's going to be acting towards the center of the track, which is going to be over there. So what have I said there? I said the weight force acts straight down due to gravity. The support force, aka normal force reaction force, acts perpendicular to the surface. The vertical component of the support force will be equal to the weight force. So this weight force is the vertical component of the support force. So this weight force is going to be equal to the vertical component of that support force. The centripetal force is the horizontal component of the support force. So we've got the support force, the vertical component is going to be the same as the weight force, which is mass times gravity, and then the centripetal force, which is Fc equals mv squared over r, is going to be this little vector here, this little bit down there. So hopefully that all makes sense. This angle here, theta, is going to be the same as that angle there. So the the angle between the support force and the vertical component of the support force, which is equivalent to the gravitational force, is going to be theta. Either remember that or be able to work it out from your little triangle. So you can just work it out from first principles if you know a little bit of trig. This is going to be whatever it is. This is going to be the other half of that 90, and then this is going to be that again. Anyway, lift force acts kind of the same way. As we can think of it in the same way as we think of these sort of questions here. The lift force is going to be what we'd call our normal force or reactive force or supportive force in this case. The weight force is going to act down again, and then again the centripetal force is going to be acting towards the center of the circle that it's making. The trick with these questions here is just basically knowing where the angles are, knowing that the weight force is equal to the vertical component of our support force, and then the centripetal force is acting is the horizontal component as well. So the horizontal component is acting at 90 degrees towards, and I'll do that in a question to the velocity as well, but we'll talk about that as we do a couple of questions. The third and final type of circular motion questions are vertical ones. So these are ones where we have something that's swinging in a vertical circle. And what have I said there? Vertical circle motion is under the influence of gravity. The object will decelerate going upwards and accelerate going downwards. So as we're going up, it's decelerating. As it's coming down, it's going to be accelerating. So the other ones we're assuming constant velocity. So this one is constant velocity, and the satellite motion is going to be constant velocity as well. This is the only one where you don't get a constant velocity. We get a change in velocity because it's accelerating downwards and it's going upwards. For these ones we usually work out the tension forces, and we'll talk about that in a second. But essentially, the typical question is the minimum speed, whenever it's at the very top, is going to equal the tension force is going to equal mass times gravity. At the bottom, the tension force is going to be equal to the centripetal force plus the weight force, the mass times gravity. So at the top, the centripetal force is going to be T plus Fg, the tension force plus the force of gravity. At the minimum speed, that is going to be equal to 0, because if you can imagine we're spinning something upwards, the tension force, as the slower we speed it, the slower that we swing it, as we're swinging it vertically, the less tension we're going to have. So if you're swinging a pair of keys on a bit of swing, on a bit of string, if you keep reducing the speed that you're swinging it, eventually what's going to happen is that bit of string is going to lose tension and the keys are just going to fall. If you remember the little cup on the string thing that I had in class where we put phones and stuff on it, and if you get it to a speed where it's not actually going around in a circle anymore, it's just going to collapse and everything's going to fall off it. That minimum speed is going to be equal to the force of gravity, or the weight force. And that's when tension is equal to 0, basically. So Fc is equal to Fg at minimum speed, we can say. Okay, let's get into some questions. We will start again at the very bottom of the sheet, because hopefully you've started at the top yourself and you're going through them. Again, 2 or 3 questions in a row per day and you will be fine. You'll get better at them as you go. If there is stuff that you don't understand, please feel free to either email me or to email me is probably the best way, or just ask a question whenever I'm doing these walkthroughs. Okay, now question 1, driving on banked corners, 2004. Using the gravitational field strength. So we've got some figures here. Let me see, where's my pen gone? Oh. Okay, so we've got some numbers. Have I got my pen? Where's my pen? Is it working? It is working. Okay, so we got some numbers here. We got 9.8 Newton kilograms, which is the same as 9.8. Quite nowadays, I think you'll be given 9.81. This is a very old question, obviously. Moana is driving home from work in her car. At one point, she drives around a bend in the roads that has a horizontal radius of 99.0 meters. Maybe I shouldn't use my little highlighter for bits like this. So we've got some information here that we need to remember. This bit, I'll highlight. We got that bit. We've got an angle in there. And we got a mass of the car, which is that number there. Okay, so it's asking us, the first part is asking us to label the vectors. So we'll do it maybe in red. And the diagram, draw a free force body diagram to show that the reaction force F and the gravitational force F acting on Moana's car. Label both vectors. Okay, so this is fairly straightforward. This is, we're just going to say the center of mass of the car is here. Oh, I hope it doesn't keep doing that. It's going to be straight down gravitational force or weight force, and then the reactive force is going to be, if I can get my pen to work properly, at a 90-degree angle. A 90-degree angle. That's a terrible one. I'll just go back again, sorry. Can I just do a little line? Maybe I can do that. Okay, we're going to have a 90-degree angle. That's going to act like, where's 90 degrees? That's 90 degrees there. Okay, I'll just share. Anyway, you hopefully get the point. So that's 90 degrees there. And then I'm going to do another one. And the weight force is going to be acting straight down. Okay, that's better. And I'll just get rid of Okay. So we got our two forces there. I'm going to label the other one now. So that one is the reactive force there. Now, if we remember, I'll just do it in a different color. The weight force is going to be the vertical component. Excuse my bad writing. The vertical component of of our reactive force here. So this reactive force, the vertical component, is equal to the weight force. So the green arrow is equivalent to the force of gravity. Okay, we've got a third force which we haven't been asked for, but this is the unbalanced resultant one. I'm going to do that in another color again. I'll just do it in blue, which is going to be this one here. Okay, so this is going to be my terrible writing is our centripetal force. This is the unbalanced force. So this reactive force is going to be equivalent to the trigonomic product of the force of gravity and the force of centripetal force. Okay, so we've got some stuff going on there. On the diagram, draw a free body force diagram to show the reactive force F and the gravitational force F acting on Moana's car. Label both vectors. So that's the gravitational force and that's the reactive force there. On the diagram, draw and label an arrow to show the direction of the unbalanced force acting on the car. So this is the centripetal force. I've already done that. I'm just gonna draw something else over here. So this, if we look down on this diagram, so what's happening is this car is going around in a circle like that. Okay, the car, if it's going in this direction here, is going to have a velocity forwards, but the centripetal force is going to be acting towards the center. So the centripetal force is the thing that's keeping it going around in a circle. So this is the FC, and that's the velocity there of the car. So the car only drives forwards, but because it's on a bank, it's going around in a circle. And that's because of the reactive force there. So again, this is looking down on top of it. Calculate the value of the vertical component of the reactive force. So that's easy. That's just our friend gravity. So again, if we can't remember what it is, it's F equals ma, and a is the acceleration given by gravity. So this one, if I've got my pen, F equals mass times gravity. We've got our mass. It is, where is it? 9, which equals 995 times 9.80 in this case, usually 8.1. Don't have a calculator anywhere near me. Oh, I know, I've got this little calculator here. 995 times 9.8 is equal to 9751, which is equal to 9751 and newtons. And that will probably be an achieved point. In terms of the forces acting on the car, explain why the car will travel around the bend. In terms of the forces acting on the car. So this is where maybe this little diagram is going to come in handy here. So we've got a velocity which is acting at right angles to the centripetal force. So we're going to talk about the unbalanced force. So say that as it's on a plane, if it's on a plane, the weight force acts straight down. It's going to have a reactive force which is acting at a 90-degree angle to the plane. There will be an unbalanced force, which will be the centripetal force, which will act towards the center of the circle. So centripetal force acting towards the center of the circular path of the car. This is the unbalanced force. So it's going to make it go around this thing, and so you need to include that the velocity of the car is acting at 90 degrees to the centripetal motion of the car, and that's why it's going around the bend. Okay, calculate the speed of the car as it drives around the bend. So what have we got? We've got our formula for this one is going to be what it's going to be. This one down here, our centripetal force is equal to the mass times the velocity squared over r. So we just need to rearrange it. Let's have a look. I'll just bring that back up again so I don't lose it. Let me see. I'll do FC is equal to v squared divided by r. So I will just do the algebra correctly so you can see what I'm doing. Do we have the FC yet? Did I work that out? No, I didn't, did I? Okay, so there's another step to this equation. Okay, so we're gonna use this one to work out the velocity. I'll just do the algebra now while I'm at it. So I'm going to multiply both sides by r. They're going to cancel out. So that's going to leave me with r times fc is equal to mv squared. And then I'm going to divide both sides by m. Let me see, go back to that one. Divide both sides by m. Oops, what did I just do there? And they're going to cancel out. So that's going to leave me with, I've now got that to v squared is equal to r times fc divided by m. So v is going to equal the square root of r fc divided by m. Now, okay, I need the fc. So the fc again, centripetal force is going to be this component of our little force diagram. So if I do it again, I'm just gonna, I've got my gravitational force that I just worked out there, which are my weight force. So I know that value there. So I know the green arrow here. I'll just redraw it over here. Bum bum bum. Okay. So I'm going to do my little bit of trig over here. This is my weight force, or well, it's the component, the horizontal component of my vector force diagram that I'm doing on the car over here. And we got that one, and we got that one. We know this angle because we're given it over here. It is 6.5. So theta is going to be 6.5. This is the right angle. Which ones do we have? So this is the adjacent. This is the opposite. So we're going to use, what are we? TOA. So we did that weird. So TOA. We're going to use TOA. So the tan of the angle theta is equal to the opposite over the adjacent. The adjacent is this number here, and we're looking for the opposite, so it's going to be the adjacent multiplied by the tan of theta, which is 6.5, is equal to that. So it's going to be 9751 times the tan of 6.5 is equal to whatever. So let's get our calculator up and see if I can do it. 9751, it's already in there, times the tan of 6.5, enter, 2147. So 2147. For this, make sure that you're in degrees and not radians. What did that say? Sorry. 2417.9, 2418, 2148, 2148, and that's newtons. So we've got our FC. We still need to put it into our little formula that we've worked out over there. So that's going to be the square root of r, if I've done my algebra correctly. Yep, I think I have. So that's going to be, well, do we know our radius? We do. Let me see, I'm just going to write out the numbers here that I've got. So I've got my radius is 90 meters. R equals 90. The mass of the car, M equals 995. Oops, 995. And our FC is 21. FC equals 2148. Okay. So then again, just put your numbers into your calculator. So I've got my FC already there. I'm going to multiply that by a radius, which is 90. And what does that equal? That equals that number. I'm going to divide that by our mass, which is 995. and that gives us that number, and then I'm going to square root it. Where's my square root function? Okay, so our answer is 13.93 or 13.94 meters per second. Whoops, where am I? Which equals 13.94 meters per second. And if I look, what have I got here? So I'm just going to look for my significant figures. 3, 3, 3. So I'm going to go to 13. Yeah, it should really just be 13.9 meters per second. 3 sigs. Boom. Okay. The next one, so we've done that. That looks like an E question, I'm pretty sure. Explain what would happen to the speed if the banking angle of the road had been greater but the friction remained 0. So we need to figure out if our banking angle goes up, what is going to happen to our velocity. So let's see. So okay, I'm just going to talk you through it. So if we go back to how we got our centripetal force, our centripetal force is the gravitational force times the tan of the angle. The angle is the angle that the car's sitting at. So if this angle increases, so we've got A times the tan of theta is equal to our centripetal force. If theta increases, what's going to happen to this number? So this is a direct relationship. If I make the angle bigger, so if I put in 9751, in fact let's just do it, I'm just going to put in 9, oops, where's my calculator gone? Clear, clear, 9751 times the tan of a bigger number. I'm just going to pick 10 for instance, and then what I'm going to get a bigger number. In fact, that's huge. So as the angle increases, the centripetal force is going to increase. If the centripetal force increases, what's going to happen to our number? So as this angle goes up, the centripetal force will increase. And if we look back over here where our formula is, what sort of relationship is going on between the centripetal force and the velocity? That's another, it's not an inverted one, it's a positive relationship. It's on the same side as the velocity. So if the centripetal force goes up, the speed will go up. So the speed will increase if the banking angle of the road is greater and friction remains 0, because if friction remains 0 and it's going around in a circle and it's not slipping down there, it means that it has to have a centripetal force that's acting inwards. It has to have an increase in velocity. So that's, you're gonna have to explain all that again. That's probably a merit or an excellent explanation. Cool. Now let's see if we can find the actual answers for this and see if we're right. Bum bum bum. Okay. Where are we? 2005, 2004. Okay. We ain't got no answers for 2004. We're just going to have to assume that I'm right. About 50-50 chance of that actually. But anyway. Okay. Let's try another one. We'll try the 2005 one. There is answers for this one. So we'll be able to see. I'm just going to clean this up a little bit so I've got a bit of room to draw. So just while I'm rubbing stuff out, I'll read out the question. We've got the London Eye is a giant rotating wheel that has 32 capsules attached at evenly spaced intervals to its outer rim. Passengers riding in the capsules get spectacular views over London, especially at the top. Blah blah blah. The capsules each have a mass of 1 times 10 to the 4 kilograms and are a distance 68 meters from the center of the wheel. So I'm just going to again just highlight some of the stuff that I'll use. We've got this mass, boom boom boom. We've got a distance 68 meters. They're traveling at this speed. Calculate the size of the centripetal force that is maintaining the vertical circular motion of the capsule about the center of the wheel. Okay, so this is a vertical circle, but it's not actually a vertical. It's not the typical vertical circle question, because in this case it's just moving at a constant speed. If we were swinging it, if it was being swung, then it would have a change in velocity and different tension forces and whatnot. But in this case, we don't have any of those, so that's pretty cool. It's nice and easy. Something on the thing. Okay, on the diagram, draw a labeled free body force diagram to show how the forces on the passenger. Hold on. Calculate the size of the centripetal force that is maintaining the vertical circular motion of a capsule about the center of the wheel. Calculate the size of the centripetal force that is maintaining the vertical circular motion. So the centripetal motion is going to be towards the center of the circle. We've got a velocity, we've got a mass, and we've got a radius. So this is just going to be Fc equals mv squared over r. So where am I? Fc is equal to m times v squared divided by r, which is going to be 1 times 10 to the 4 times 0.26 squared divided by r. Let's find our calculator. Where have I put it? Oh, my calculator disappeared somewhere. I'll just find it again. Anyway. Bum bum bum. Aha. There we go. Boom. Alrighty. Clear. Oh. Exit. Menu. 1. 1 to the 4 times 0.26 squared, all divided by, what am I dividing it by? R, which is 68. 9.94, which equals 9.94. We're talking about a force, so it's going to be newtons. On the diagram, draw a free body force diagram to show how the forces on the passenger combine to give the centripetal force causing her to move in a circle. Okay, so what do we got? We've got our weight force acting straight down. Whoa, that's a nice arrow there. Weight force acting straight down. We've got our centripetal force, which is acting towards the center. Bum bum bum. And then why we've got a third force somewhere. What is that force? So the third force is going to come. So why is she not? What should be happening here? So she's being moved in a circle. So she's moving in this direction here. If I can do it with a different color pen. Okay, so she's moving in that direction there. There's a weight force acting down, the centripetal acting force that way, but there has to be a third force in there somewhere, and the third force is actually just going to be the friction that she's got from her feet. So that's going to be the frictional force, which is acting on her feet. F. So we've got a little triangle there. We've got our weight force, we've got our centripetal force, and we've got our frictional force going on there. And that's the three forces that are going to be causing her to move in a circle. If she didn't have the frictional force, what she'd do, she just slide that way, or she would just stay where she is actually, and the thing would slide from underneath her, and she would fall to her death. Okay, I think that's everything on that question. Okay, next one, space, the final frontier. The universal gravitation. Oh, I should actually look at the answers for that last one. Let's have a look if I can find them. Okay. Where am I? Oh, right. Oop. 9.9 newtons was the answer. I think that's what we got, wasn't it? Let's see. 9.94, yep. And recognition that gravity and another force contribute to the centripetal force. So the centripetal force is going to be the vector sum of the gravitational and the frictional force. Diagram to show the gravitational force and another force combining to give a centripetal force that acts towards the center of the wheel. The other force is recognized as the friction acting on the person's feet. So yeah, I think we got there. My diagram was not as neat as that one, but it is still probably all right for a pass, I think. Okay, let's keep going. What's our time? 25 minutes left-ish. Universal gravitational constant is 6.67 times 10 to the negative 11 newtons. Mass of the Earth is that. We've got a space shuttle Discovery is in a circular orbit, which is that. Boom, boom, boom. And this time it's actually given us from the center of the Earth, which is really nice, so we don't have to do any adding. The diagram shows the shuttle and the telescope system orbiting the Earth, blah, blah, blah. Name the force that is keeping the shuttle telescope system in the circular orbit and state the direction in which the force is acting. So something is orbiting around the Earth. The force that you should think of is, of course, gravity. Gravitational force, which gives the centripetal force. So we're going to say gravitational force, and it's going to act towards the center of the Earth. So it's going to be boom, 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 F, G. Okay. Calculate the value of the acceleration due to Earth's gravity, the strength of Earth's gravitational field at this height above the Earth's surface. Write your answer to the appropriate number of significant figures. So what do we know? We've got the gravitational constant, so we know a couple of things here. What do we got? We got what are we looking for? We're looking for the acceleration due to gravity, which is actually this equation here. So force is equal to mass times acceleration. In A we usually just change the G. So we're looking for G, and we're going to also use this one here. This is the other common one. We might use this one as well in these questions. I'm not sure yet. I haven't thought this right through. But anyway, that's gonna, yeah. Okay, so what are we looking for? We're looking for F equals mg. F is equal to mg, and we also know that F, big F, G is equal to big G, big M, small m. So the mass of the orbiting thing and the mass of the thing that's orbiting. No, sorry, this is the mass of the thing that's being orbited, and this is the mass of the orbiting thing, usually, r squared. And we can also say that F is equal to Fg, so therefore mg is equal to big G, big M, small m over r squared. And if you know your algebra, you know that we can multiply. I'll just do the algebra. Boom, boom, boom. I'm going to divide both sides by small m because I want this m to get rid of. Boom, boom, boom. Those two cancel out. Those two cancel out. So I'm left with the acceleration given by gravity is equal to gravitational constant multiplied by the mass of the Earth divided by the radius of the orbiting thing squared. So what have I got? I've got G, I've got M, I've got r squared. I just need to put them in my calculator. I'll just write out the stuff here. So G is equal to 6.67 times 10 to the negative 11 multiplied by the mass of the Earth times 5.98 times 10 to the 24, all divided by the radius squared. So that's going to be 7.7 times 10 to the 6 squared. Let's just do it in our calculator. Clear. 6.67 to the, what is it, negative 11. My writing's terrible. Negative 11 multiplied by 5.08 to the 24 divided by 7 times 10 to the 6 squared. And that's going to give me 6.91. So does that make sense? Does it make sense that the force of gravity is less than the force of gravity that we know, but pretty close to it? Yep, it is. It does make sense because it's further away from the surface of the Earth, so it is going to be less. You feel less acceleration at the further out you go, until you feel virtually nothing. If we had a bigger number here, it wouldn't make sense, so we would know that our answer is wrong. So that's a nice wee check, just to check. So it's, what is 6.91? Okay, we're happy. Calculate the blah 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 blah. Write your answer to the appropriate number of significant figures. Okay, I think I've just accidentally done it. This is 3, that's 3, that's 3. It's going to be 3 6. Was the, oh, I didn't round it, did I? 6.915. Look at that. What an idiot. Delete. I'll just finish it off there. So 6.915, 6.92. What are we talking about? We're talking about an acceleration, so it's going to be meters per second squared. 6.92 meters per second squared to 36. Okay. Weight is felt as a reaction force. Explain why an astronaut in the shuttle feels weightless while in orbit about the Earth. Okay, so the astronauts within the shuttle. Okay, so maybe I'll just draw a very bad shuttle. Boom, boom, boom. And we got an astronaut in the shuttle. Okay, so on Earth, he would have a weight force, and that weight force would cause a reaction force from the floor, which he would feel through his feet, and that's what he would feel. If he's orbiting the Earth, brum, 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 what's happening is that the shuttle is falling towards the Earth, and he is falling towards the Earth with the same acceleration. So that's the acceleration given by gravity. So everything's basically falling, but it's falling in a circle continually, round and round and round and round. So because the shuttle is falling at the same rate or the same acceleration as the astronaut inside it is falling towards the center of the Earth, it means that relative to each other they are not accelerating. So neither the shuttle or the guy are feeling any force exerted from each other, because they're both falling basically at the same rate towards the center of the Earth. Now, okay, let's have a look at, there's a second question here. Part 2. Phobos is one of the moons of Mars. It orbits around Mars at a mean radius of 9.38 times 10 to the 6. That is a mean radius. With a period of 2.76 times 10 to the 4 seconds. From this information, calculate the mass of Mars. So what? Okay. Oh, yep. So this is a really common one actually, because what we want to know, the trick to this question is that FC is going to be equal to FG for orbiting objects. So my formula for FC is, if I bring it over here, mv squared over r, and our formula for FG is gmm over r squared. So what I can say is, mv squared divided by r is equal to big G, big M, small m over r squared. Okay. If I start to do a little bit of algebra, what I can do is I can get rid of some of the I can simplify this a bit, because if this m here is going to cancel out that m over there, so those two m's are going to cancel out. So I can prove it. All you need to do is to divide both sides by small m. So let me just do that. Bum, bum, bum. Yep. Where's my pen? It's over there. So I'm just going to divide. I'm just going to divide both sides by small m. So that means those m's are going to cancel out. The other common thing that happens at this stage is people multiply by r. So I'm going to multiply both sides by r. those r's are going to cancel out, and that square is going to cancel out. So you're going to end up, you're going to end up with, why does it do that? Going to end up, one more time, you're going to end up with a formula that is going to be v squared is equal to g times m over r, and then you usually square root both sides to get velocity. So this is a common one that you'll use, or it might come up. Velocity is equal to the square root of the universal gravitational constant times the mass of whatever object divided by r. So we've got, in fact I am going to use it here. So I'm looking, I'm just going to go back a step. I'm going to erase that one because I don't actually need to go that far. I do want to find big M, so this M value is what I actually want from the end of my equations. So I'm going to continue on with the algebra. Again, multiply both sides. Oh, I'll do a different pen color. That's probably an easier way to get different pen colors. Excuse me. So I'm going to multiply this side by r, that side by r. They're going to cancel. Where am I up to? And then I'm going to divide both sides by big G. So my end formula is going to be radius times the velocity squared divided by the gravitational constant is equal to the mass of the planet Mars. I still don't have my velocity here, so I need to figure that one out. The velocity of something which is orbiting something. So if I'm just going to clear up this side a little bit because I'm going to draw some stuff here. Get rid of my plane or my thing. Okay. So we've got Mars, and we got Phobos orbiting it. Okay, and if I imagine it's going to go around this planet once, and that is going to be the period which is given to me. So the period is 2.76 times 10 to the 4 seconds. So this is kind of the key to figuring out the velocity, because I also know the radius, which is the mean radius is 9.38 times 10 to the 6. The reason why they say the mean is actually because it varies. It goes in and out a little bit, so they average it, make a mean. Not that it's amazing. So that is the radius. And we also know that the radius is related to the circumference, which is the distance that this thing is traveling by. So c is equal to 2 pi r. And you need to know this. This is not given to you. It's just something you must know. 2 times pi times r is the circumference, and that is going to be the distance. And we also know another equation, where we should from level 2, or maybe you don't, but anyway, velocity is equal to distance divided by time, meters per second. So so what I can say is the time is the period, and the distance is this. So my velocity is equal to 2 pi r divided by the period. Alright, so what I need to do is I need to work out this value and then plug it into this equation here to get my answer. So 2 pi r, 2 pi times, what's the radius? 9.38 times 10 to the 6 divided by 2.76 to the 4 times 10 to the 4, and that's going to give me a velocity of 2,135 meters per second, which sounds fast, but it is a satellite, so it is probably right. Oh, I've just realized that you can't see the bottom of that screen. Shoot. Can I move that up? Okay, this is the little bit here I was doing. So velocity is equal to d over t, which is meters per second. The circumference is 2 times pi times r. The velocity is going to equal 2 pi times r divided by the period. So the time The time is equivalent to the period, which is 2.74. Blah blah blah, and we've got an answer of 2135.37 meters per second. We need to put that into our v squared over g equation, so I'm gonna square that. Let me see, answer squared, and then I'm going to multiply it by the radius again, which is 9.38 times 10 to the 6, and then I'm going to divide it all by the gravitational constant, which is 6. What does it say? 6.67 times 10 to the negative 11. 6.67 to the 11, and that's going to give us a number that is not right. I know this is not right because the mass of Mars is not 64 kilograms. So what have I done there? I've made a mistake somewhere. Oh, I didn't do it. It's 10 to the 11. Okay, so I need to go back. How do we go back in this thing? Delete to the negative 11. Okay, that's better. 5.78 times 10 to the 20. So the mass of Mars is 5.78. Mass of Mars. M is equal M. Why is everything disappearing on me? M is equal to I've forgotten already. 5.78 times 10 to the 20 kilograms, which is a big number and it's a big planet, so that sounds about right. Okay, let's just check our answers one more time. Boom, boom, boom. Where am I up to? Which one is this? 2000 and what? Shoot. 2006. Okay. The force is the gravitational force that acts towards the center of the Earth. We've done that. We got it right. 8.14 newtons. Did we get that one right? I can't remember. Did we use the right thing? mg equals that, so we hopefully put the right numbers in. Did I get the right answer? I can't remember. Did I rub it out? Don't know where it is anyway. I'm just going to assume I got it right. The reaction force on the shuttle and the astronaut gives them the sensation of weight because the astronaut and the shuttle are falling freely. This is the one of this is the weight is felt as the reaction force. There's no apparent weight. Oh, hold on a second. I've got the last one wrong. Why have I got the last one wrong? Okay. FC m equals v squared over r. Yep, over g. Got that right. I've done a calculation problem somewhere, or made a calculation error somewhere. 2135, is that what we got for our velocity? Where did I put it? Did I write it down somewhere? Maybe I deleted it. Did it? Okay, so we'll just ignore the actual number there and see if I got the formulas right, because again, if you've made a calculation error but you've laid out your working in a sensible way, you're still probably going to get the number of points right. So if you've done this bit here, which we have done down there, and I've put my numbers down somewhere, which I have done as well, I've just made a calculation error somewhere here. Oh no, it's this question here that I'm doing. But anyway, this is the right way of doing it. V is equal to d of t. We got the right idea there. I think this was the number that we came up with. And then m is equal to v squared r over g, which is what we did. I've obviously just had fat fingers and typed something in wrong. But that's the right way of doing it, which is good. Centripetal force is a gravitational force. Fc equals Fg. And that is a nice E point. Okay, moving on. Right, we got a golf ball. Another universal gravitational constant. In fact, I'm just going to skip that one because that's very similar to the last one. I'm going to do a That's another gravitational. I'll do this plane one because we've only done one of these ones so far, and this is another type of one. There is a third type of one. I'm not sure if I'm going to have time to do it, but anyway. Sam enjoys flying vintage airplanes. One of the planes that Sam flies has a mass when operating of that. In order to turn the plane in a horizontal circle at constant speed, Sam tilts or banks the plane at an angle of that. The free body forces on the plane are shown in the diagram below. So we've got the force due to gravity, which is straight down, and we've got our lift force, which is acting at an angle to the horizontal or to the vertical, which is going to be that angle there, 22.5. So the vertical component of a lift force is going to be the same as the force due to gravity, and then we're going to have a centripetal force which is acting towards the center. I might just draw, and I'm probably going to ask me to draw it in a second anyway. No, it doesn't, so I'm going to draw it myself. So we've got the vertical component of that, it's going to be equivalent to Fg, the weight of gravity, and then we've got a centripetal force which is acting inwards towards the center of the circle, and that's going to be our unbalanced force, our centripetal force. Show that the size of the vertical component of the lift force is 6230 newtons. So hopefully by now you realize that this is going to be our force of gravity. So all we have to do is multiply our acceleration, F equals ma, F equals m times g. We know our mass, it's 635. We're going to multiply that by 9.81, and we're going to get, what are we going to get? Mm-hmm. 6229.35. So that's the same as that. Calculate the size and the direction of the resultant force on the plane during this turn. So the direction is going to be towards the center, which in this case is to the left. So we need to write that down somewhere there. Towards the center, to the left, in brackets I would put. And the size is going to be this trigonometric function of it. So if I do my little thing, this is going to be 22. This is going to be the angle here. It's going to be the opposite. And again, this is the adjacent. So we're going to use our SOHCAHTOA. And we're going to use TOA. So tan of the angle is equal to the opposite over the adjacent. We want the opposite, so it's going to be the adjacent times the tan of the angle is equal to the opposite. The adjacent is what we've just worked out, 6230 times the tan of the angle, which is 22.5. So that number times the tan of 22.5, and we got 3475. So the centripetal force is equal to 3475. Oh, sorry, I've just realized again that you can't see the things that I'm doing down there. I've just written out the adjacent tan theta equals to the opposite, and it's 6230. In fact, I've just used the number that was in my calculations before. Remember to use the number that is calculated, not the number that's rounded. Tan 22.5, and that's going to equal, I've forgotten already, 3475. Bum bum bum. 3475 newtons. To the left, or center of circle. Okay, in another constant speed horizontal turn, the plane has centripetal acceleration of 2.5 meters per second. Calculate the angle of banking of the plane in this turn. Okay, so we've got a centripetal acceleration of 2.5 meters per second, and we want to find out theta, the angle of banking. So this, we've got the weight the weight force is going to remain the same. So I'm just going to redraw this here. So our centripetal force, we got our lift force, Fc, Fl, and then we got our weight force, which is acting in the opposite direction to weight, but anyway, our gravity force. That's going to be the same as it was before, so it's just going to be, what did we say it was? 6229 point something something something. That's going to be the same. This is going to increase, is that right? For the centripetal, in another speed turn, the plane has a centripetal acceleration of 2.5 meters per second. Okay, so we don't actually know if it's going to increase or decrease, but we're going to work out this here. So the centripetal acceleration is 2.5. Okay, if I want to work out the force from this one, force is equal to mass times acceleration. I know the acceleration is 2.5, so the mass is not changed. It is going to be 635. So Fc, the force, is going to equal 635 times 2.5. Clear. 1587.5. You can't see my calculator. So Fc equals, my memory is just terrible today. 1587, 1588, 1587.5 newtons. So I want this angle. I've got this side, it's 6.229, and that one is now 1587. So how to work out the angle? I've got the opposite, boom boom boom, I've got the adjacent. I want the angle, so I'm going to use tan again, but it's going to be tan of theta is equal to the opposite over the adjacent. So I'm going to go, the theta is equal to the inverse of tan to the -1, opposite over the adjacent. So what did I just work out? I just worked out the opposite, so I'm going to divide that number by the adjacent, divided by 6, what was it? 6230 equals that, and then I'm going to do the inverse tan of the answer, and that's going to give me an angle of point. Does that sound right? Opposite over the adjacent, 0.2495. Have I done this question correctly? Let's have a look at the answer. What year are we up to? 2009. Okay. Oh, I made a mistake somewhere. Okay, 2.5 tan of theta equals 2.5. I've done that right. Tan of theta. Have I not just done? Is that what have I done there? Tan of theta equals that. Hold on. Oh, I just made a mistake with my calculator. Shift tan 0.25.24. Why is that coming up differently? Am I on radians? I'm doing something weird with this calculator. I'm not sure. This is the first time I've used this USB one. How am I doing? And I'm not really good at FX 960 calculators because I don't have one. I'll have to try that again. Anyway, that's the answer, 14.3. Why? I'm just going to do it on my own calculator here. A second. Inverse tan, shift tan, 0.25 equals, 14 degrees. Okay, so I don't know why it's working out wrong on my calculator. So it is the tan, this is all correct, which is equal to 14 degrees. Okay, cool. Last little bit. I think I'm at an hour already here. I'm going to quit in a second. For a plane to tilt in a horizontal circle at a steady speed, it is necessary to tilt the plane by considering all the forces that act on the plane. Explain why this is the case. Okay, so we've got a weight force acting downwards, we've got the lift force acting upwards, and we've also got a centripetal force acting inwards. So if we look downwards on the plane, so the plane is going around in a circle like that. The centripetal force has to act at a 90-degree angle to the plane's velocity. So the propellers of the plane are just pulling the plane forward. So the plane is just going forwards the whole time. The plane's wings are angled so that the centripetal force will act towards the center, and that's going to be the horizontal component of the lift force. So the lift force is caused by the plane tilting its wings. The horizontal component of the lift force acts towards the center of the circle, which causes the plane to go around in a circle. And that's basically everything there, I think. Let's have a look at what they say. To move in a circle at constant speed, the plane needs a centripetal force. This must be an unbalanced force that acts at right angles to the velocity of the plane. This can only be provided by the horizontal component of the lift force. There's no other way, blah, 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 blah. Propeller makes it go forwards, friction drags it back, weight force pulls it down. So, what have they said there? The tilt gives the horizontal component of the lift force, which provides the centripetal force. Okay, so that's the bit that I said. Discusses the effect. At right angles to the velocity and the direction of the centripetal force. Okay, so I think I would have got the either. Discusses the effect of one other force, drag, friction, weight, thrust. I did say that weight acts straight down, so I don't know. I definitely get merit. Might have got neither. That's an odd one. Okay. I am not going to be doing another video tomorrow. I will do one on Monday after school at some point. Hopefully that made sense. And you could see the actual calculations this time. I will be doing what's next on the cards. Rotational motion, I think, is the next one up. So I'll put a little schedule up and see you all on Monday. Thank you. Catch you later if I know how to close this thing off. Bye.